Okay guys, so we're going to have a look here at a video on the acid-base equilibrium. So we're just going to deal with calculating the pH of weak acid. This is, I suppose, a video that you maybe want to watch prior to looking at the buffer videos. In fact, definitely prior to watching the buffer videos. So we're going to look at how do we actually calculate the pH of a weak acid. Now, you'll often see a weak acid represented as HA. So when you do see that term HA, that's what we're talking about. When you see square brackets HA, well then we are talking about the concentration of that weak acid. Okay, now the reason why we use HA is because H stands for the hydrogen aspect of the weak acid, and the A stands for the anion part of the weak acid. So you'll often see this sort of thing here of the weak acid dissociating without these charges on the left hand side into that and that. So for example, if I talked about ethanoic acid, the A minus would be the ethanoate ion as so, and of course the H plus is just the H plus. So the HA is just a generic way that we'll use to refer to weak acids primarily. Now you've done the strong acids, and if you remember when we did strong acids, we worked out the pH, okay, by taking the hydrogen ion concentration minus the log of the hydrogen ion concentration was equal to the pH. Now you might say to yourself, well, okay, so when I did, for example, hydrochloric acid, strong acid, and I know that 100% ionizes to hydrogen ions and chloride ions, and if I had, let's say, 0.1 molar, 0.1 mole per decimeter cubed hydrochloric acid, because it's a 1-to-1 ratio, my hydrogen ion concentration would be 0.1, and all I would do there would be minus the log of 0.1, and that would give me the pH of that particular acid. If I had a diprotic acid, sulfuric acid, for example, would be the one that we would use frequently. Gives 2 protons per mole of the sulfuric acid. So if I had 0.2 molar sulfuric acid, I would have 0.4 molar or mole per decimeter cubed of the hydrogen ions. So this time it would just be minus the log of 0.4 and give me the pH of that. And you might say, well, okay, well, how come then, sir, if I have a weak acid such as ethanoic acid, and I have it at 0.1 molar, okay, and why am my hydrogen ion concentration then not just 0.1 molar, and why do I then just not do minus the log of 0.1 to give me the pH? Well, the reason is this: because we know that weak acids do not ionize 100%. So therefore we can't make this connection anymore like we did with strong acids between the concentration of the acid and the concentration of the hydrogen ion. We don't know what the concentration of the hydrogen ion. You know, does the weak acid ionize 50%? We talk about it ionizing partially, but does it ionize 50%? Does it ionize 1%? Does it ionize 20%? We don't know the answer to that, so we've got to get the answer to that in order to actually get the concentration of the hydrogen ions in the weak acid, and therefore to minus the log of that value to get the pH. So it's a whole different approach calculating the pH of weak acids compared to calculating the pH of our strong acids. Strong acids are very easy to do. Okay, so this is where the acid dissociation constant comes in, which is called the Ka. Now, the Ka basically gives me a measure of the extent of dissociation of the acids, so ethanoic acid, for example, up here would be given as a Ka of CH3, CO minus, concentration of that, upon the concentration of the hydrogen ions over the concentration of the acid itself. So in other words, the larger the Ka, the more I have on the top line. So the further, you can see from my equilibrium, I'll just tidy this up perhaps a little bit. Okay. You can see if I was referring back to my equilibrium above, the larger the Ka, the further the equilibrium lies in that direction, because the higher the concentration of my top line, and the smaller the equilibrium, well then the smaller my Ka, the further my equilibrium lies to that side. So if I can calculate the concentration of these values, okay, then I can rearrange this equation to allow me to calculate the H plus ion concentration, and that in turn will allow me to calculate the pH. Okay, so we have a few assumptions that we need to take or need to understand here before we go any further. Right, so these assumptions just allow the maths really at A level to be a little bit more straightforward than it might otherwise be. Right, so assumption number one is that at equilibrium, the concentration of the HA, okay, remember I said earlier, the unionized HA, okay, is equivalent to or equal to the ionized. Okay, so in other words, if the examiner said you started off with 0.1 molar ethanoic acid and you put that into, allowed that to ionize, well then you just use that 0.1 molar as your value for here. Now, obviously whenever an acid ionizes, the concentration is going to drop a little bit because some of it dissociates into its ions, but for the purpose of this we just treat the two things as being the same. The other thing that we're going to do is assume that the concentration of the H plus is equal to the concentration of the A minus. So in this case the A minus is the ethanoate ion, okay, and you might say, well, I mean, if we look at the equation up here, the A minus and the H plus are made in a 1-to-1 ratio, so they must be equal. But what you perhaps don't understand at the minute is that when acids are acids, they are in water, and water itself ionizes a little bit, okay, and when you do your strong alkali calculations, you'll see this, to produce their own H plus ions. So in actual fact, as well as having the H plus ions that we have here, you will also have some H plus ions from water. Okay, now for the purposes of our calculations, we basically ignore these, okay, and we say that the H plus and the A minus are made in a 1-to-1 ratio up here, and therefore are exactly the same concentration. So it just makes the maths of the whole process a little bit easier for A level chemistry, otherwise it would just get too challenging. Okay, right, so that's fine, that's our Ka, that's what our Ka is, it's a number. So if I was to say to you the Ka, for example, for ethanoic acid that I have on the board is, I think off the top of my head, 1.74 times 10 to the minus 5, so it's an exceptionally small number. So what that tells me is that the amount of dissociation that happens with ethanoic acid, and most weak acids are similar, is very, very small. Okay, so we can see really why we can just go minus the log of the 0.1 from up here to get the pH. It's nowhere near 0.1. Right, so let's have a look and see how we rearrange this equation then to make H plus our subject, and from there then to get the pH, because that's essentially what we need to do. So we need to make H plus our subject. We know that H plus, okay, and the A minus, I'll just write it out for ethanoic acid. We know that they are equal, so therefore they are equal to the Ka multiplied by the concentration of the unionized ethanoic acid. Now, because I know that these two are equal, what I can say therefore is that H plus squared is equal to the Ka multiplied by the concentration of the COOH. So if you're mathematically on the ball, we'll see where I'm going here. I want to get H plus Okay, so therefore I square root both sides. Ka times CH3COOH, concentration equals H plus, and then we know that we minus the log of that to give us the pH. So no matter what information we get, we want to try and find out that we'd probably be given that, although we might be given a thing called pKa. We need to rearrange it all and then get our H plus ion concentration. And once we get our H plus ion concentration, then we are, from there we're able to do our pH, simply minus the log of it, and that's it really. Okay, right, so let's have a look there. I spoke a couple of seconds ago there about a thing called the pKa. Now pKa is kind of like pH, okay, but for weak acids. It gives us a whole number, okay, which allows us to compare the strength of a weak acid to that of another weak acid, right? We don't really need to know very much about it, but all we need to know is that the Ka is equal to 10 to the minus pKa. So that allows us to convert pKa, if we're given that, into Ka. And we have to be able to do that because obviously you can see from the formula above, Ka is needed in that formula, and if we don't have Ka, we certainly aren't going to get our pH. Okay, so that's really, you do need to know that. pKa, if you are asked to get pKa, that is minus the log of the Ka. So you can see a relationship a bit like pH equals minus the log of the H plus there, and you can see down here that unlogging that, if you like, is 10 to the minus pH. So you should have met that. You should have met that before, okay? But this and this are probably new to you in this video. Okay, so that's all the sort of the theory about it. That's why we can't treat weak acids in the same way as we treated strong acids. That's how we write a Ka expression for, I've done one there just for ethanoic acid. Examiner will constantly or commonly ask you, just to write a Ka expression for a particular acid. That is how we do it. You can see there at the end of the green arrow, you just adapt it for whichever acid the examiner asks you for. These are the two important assumptions that you have to be able to write about. Now they'll probably just ask you what are the two assumptions that you make here, but you have to know them anyway in order to be able to find the value or find the concentration of the HA for the particular question that you're being asked to do. Okay, so let's have a look. So we'll just do a few of these. They're not really very difficult to be honest with you. You should be able to find lots of them in your chapter 8 of your calculations textbook and in your notes. So we'll start off with a couple of really nice simple ones, and maybe you want to pause the video yourself and do some of them and just check your answers off mine whenever it okay, so let's have a look at some calculations. So we'll look at first one we've got. We'll take good old faithful ethanoic acid. So the examiner is going to tell us that we have got to calculate the pH of 0.1 molar ethanoic acid. Okay, and the Ka of that, I think I set it up above, was 1.74 times 10 to the minus 5, and that is moles to the dm to the minus 3. You can work out the units from the Ka above, of course. Okay, so all we would have to do there very simply is we can plug our values in, or we can go straight to the end game, which would be this equation here. But let's just do it stepwise first of all, so that we can sort of see where everything's going. So we've got our it should be a plus up there, by the way. Let's write the Ka first of all. Imagine the examiner's asking us to write the Ka here for a mark at the start of the question, which they would frequently do. So that would be the Ka. We would probably get a mark for that. Okay, we put in our values that we actually know here. So what do we know? Well, we know from here that this is 0.1 molarity. So that's pretty straightforward. That's really all we know at the minute. So we rearrange this into H plus, therefore equals 1.74 times 10 to the minus 5 times 0.1. We would square root that. That gives us our H plus ion concentration. And of course all we do then at the end of that is to minus the log of that. And when we minus the log of that, that gives us a value of 2.88 is our pH in this instance. Okay, so that's it really. So there's ones that get a little bit trickier than that, but the principle is there. So we'll have a look at another one here. Okay, so this time we've got to do the same thing again. We've got to calculate the pH, which is frequently what they'll ask us. Okay, we have this time a concentration of 0.2 molar. Our acid this time is hydrofluoric acid, and we have been given in our question a Ka of 5.62 times 10 to the minus 4. And again, you could probably pause the video now, have a go at this, and just come back and check that you got the right answer. Okay, so all we would be doing there is H plus is equal to the square root of 5.62 times 10 to the minus 4 times 0.2, and then we would get the answer to that and minus the log of it, and we should get an answer of pH 1.97. Okay, so hopefully you were able to do that. Right, let's have a look at, so that was number 2, let's have a look at a third one. Okay, so this time we've got methanoic acid, which is HCOOH, you'll know that anyway. Our methanoic acid is given to us at a concentration of 0.05 molar, and we've been given a pKa this time, which is 3.75. So the only difference in this one and the ones that we just did, we don't get Ka, which we need, so we do pKa, Ka equals minus 10 to the minus pKa. So our Ka comes out there at a value of 1.78 10 to the minus 4. Okay, which seems reasonable. Okay, if you get a crazy looking number there, you might want to have a look at it. Okay, and then from there we've got our HA already. So again, we do our rearranged equation, which we had from earlier. So that's 1.78 times 10 to the minus 4 multiplied by 0.05. Don't forget to square root the answer to that, and when we do that, then that is our H plus ion concentration, which we would then minus the log of, and that'll give us 2.53. Okay, so again, let's have a look at another one. Okay, so we're calculating the pH of nitrous acid, HNO2. Okay, 0.05 molar nitrous acid, Ka 4.57 10 to the minus 4. So I should really write the Kas for these as I go along, I suppose. So HNO2 will dissociate to H plus, of course, plus NO2 negative. So my Ka, which is usually 1 mark at the start of the question, would be as so. Okay, so I'll get your mark. Okay, my values here then, my Ka is of course 4.57 times 10 to the minus 4. Okay, equals the H plus, I can just write H plus squared over my nitric acid is 0.05, or nitrous acid, sorry I should say. So therefore my H plus ion concentration is equal to the square root of that 4.57 times 10 to the minus 4 times 0.05. Again, I minus the log of that. Okay, and that will give me an answer of 5.5 4.56. Okay, pretty straightforward. Again, I'll do another one, and maybe you want to pause the video when I write the question on, and then do the question yourself. Okay, so let's take propanoic acid this time. So C2H5COOH. We have a concentration of 0.1 molar, we'll say, and we have been given a pKa equals 4.87. So you might want to have a go at that now yourself. Okay, I'm including writing the Ka, so we'll write the Ka equals C2H5COO minus, in square brackets of course, upon the H plus, okay, square brackets, over the C2H5COOH. Okay, perfect. Right, we want to get the Ka, so remember the Ka equals 10 to the minus 4.87 in this one. Okay, so we get the Ka worked out at 1.35, 10 to the minus 5. That's an important value. We need that, of course. We go back over here and rearrange our equation to make H plus the subject, and we put our Ka multiplied by our 0.1 is the HA concentration. We will minus the log of our answer there. Okay, and that gives us a final answer of 2.93. So our pH there is 2.93. Okay, so I'll put another couple on the board, and I'll just put the answer up alongside it. And you can probably have a check of these. You can maybe want to write the Ka just to practice writing Ka as well. So let's say we have, again, we're always calculating the pH here. We've got 0.02 molar hydrochloric or chloric 1 acid. So that's a Cl, sorry. Okay, and we've got a Ka given to us at 3.7, sorry, that should be a 272 times 10 to the minus 8. So a really very small Ka in this particular. So you probably want to pause the video there and have a go at that one. Okay, and I will just pop up the answer here. Okay, so the answer to the pH of that was 4.56. Alright, so we'll have another go, and I'll go another one. We've got 1.00 molar. Okay, we're going to use a odoethanoic acid. Again, practice writing the Kas, guys. We'll just do the calculation. Okay, this has got a Ka here of 6.76 times 10 to the minus 4. Okay, so have a go again. Pause the video there, have a go at that. See how I'll write the Ka for this one actually, because it might be causing a few people a bit of difficulties. Okay, so that's the Ka, and the pH for that comes out at 1.59. Alright. So last one, I'll do one more. Okay, and that should do us, I think, if we can do all of these. Again, you can restart the video and stop them when I put a question up and do the question. So again, we're calculating the pH. This time the pH of hydrocyanic acid, HCN, we say it's 0.250 mole per decimeter cubed, and we have our pKa at 9.4. So again, if you want to pause the video and have a go at it and then check. Okay, so the Ka for this would be H plus Cn minus HCN square brackets. Okay, that's your Ka. Or sorry, your Ka expression. Your Ka itself is calculated out of 10 to the minus 9.4 in this instance. So that gives us a value of 3.98, 10 to the minus 10. 98 times 10 to the minus 10. Okay, so that's everything we need to know there. We rearrange our equation. Okay, equals the square root of, it's 0.25 multiplied by 3.98 times 10 to the minus 10. Gives us our H plus ion concentration, which we will of course minus the log of, and that gives us 5 pH of 5.00. Okay, so there you go. We've dealt with weak acids there. Hopefully that helps with any queries or problems that you were having.